Section 6.4, graphs of sine and cosine functions. So in this section, we're going to only focus on graphs of sine and cosine. In the next section, 6.5, that's we're going to do or look at the other trig functions, tan, cotan, secant, and cosecant graphs. Let's start with the graph of y equals sine x and watch how I'm going to graph it. Every person graphs it slightly different. I'll show you my method, which I believe is one of the simplest methods. Now, the way the graph of trigonometric functions works is that at some point you draw the curve, and then at some point it starts repeating itself on both ends. So from the time where it starts and you start graphing it until the time where it starts repeating itself, that's called one period or one cycle. So for now, we're going to look at, and we're going to come back and see why. So the period for sine and cosine is always going to be 2 pi. That's the length of one period or one cycle. So the period or cycle is 2 pi. So as soon as I know the period or how long the length of the period, then I can try to find out what points I want to use to graph this function. So I'm thinking about the same way as I graph algebraic function, like a straight line or a parabola or any other algebraic function. We used points in the past to graph those functions. Same thing I'm doing with trigonometric functions is how to graph sine and cosine using points. And this is how I look at it. So let's say it's 2 pi. So you can start at any point you like. I usually go at 0 first, from 0 to 2 pi. This is a 2 pi period. The length of the period is 2 pi. And what I'm going to do here, from 0 to 2 pi, I'm going to take the point in the middle, which is pi. So you average 0 and 2 pi. You add them together, divide by 2, which is pi. And then I average 0 and pi, that gives me pi over 2. And pi plus 2 pi over 2, 3 pi over 2. I got 5 points, and that's all I need, 5 points. So now these 5 points, those are actually the x values. 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now, I need to find their corresponding y values. So to do that, you substitute 0 into the original function. So what is sine 0? Sine 0 from previous sections is 0. Sine pi over 2 is 1. Sine pi is 0. Sine 3 pi over 2 is -1. And 2 pi is also 0. So I got 5 points that I'm going to plot here. 0, 0 is one of them. Assume 1 here, -1 there. Pi over 2, 1. Pi 0. 3 pi over 2, -1. So let me rewrite this a little bit higher here. -1. And then 2 pi 0. So then this goes up. It goes like this. That's the graph of y equals sine x over one cycle, one period, 0 to 2 pi. So does it stop here? The answer is no. It's gonna go on. I'm gonna like draw it with dotted lines to show you that this is gonna repeat on and on on both sides. So this one here, I expect this to be -pi. And then the one on the left is -2 pi. So what happened here? This is the graph. That's all we need. You need to know the graph. But we can analyze the graph and get more and more information about it. For example, we can find the domain of this. What's the domain of y equals sine x? It's all real numbers from -infinity to infinity. Or you can write like this. That means all real numbers, or the set of all real numbers. Range, it went from, it's oscillating between -1 and 1, from -1 to 1. We can find the the x-intercepts. I see 0 is one of them, pi, 2 pi, negative pi, negative 2 pi. So in general, you can say it's at k pi, where k integer. What about the y-intercept? Y-intercept is only 1 point, 0, 0. So at 0, 0, it's the y-intercept. Also, notice something. This function, it is an odd function. Odd function means sine of negative x is negative sine of x. If you remember, we called them even odd function in previous sections. And hence symmetric about the origin. The graph of the function is symmetric about the origin. Another thing we can learn here is called the amplitude. The amplitude, it tells us how far it goes up and down. So if you look at the maximum point the graph reached, it's 1, and the lowest is negative 1. So that's a length of 2 amplitudes. So we can say, which is 2. So 2 amplitudes is 2. So this tells us that the amplitude for this function is 1. And we will give you a formula how to find this later on today without even looking at the graph. So that's all the information you need to know about the graph of y equals sine x. Now what we're going to do is we're going to use basically some kind of transformations to sketch a graph for other functions related to sine x. So let's say 2 sine x. If I'm asked to graph this, how do I graph some function like this? And I'm gonna write down the ones that we're gonna work on. What about there is a negative in the front? Or what about if I change the number that is being multiplied by x instead of 1? Let's make it 2. So how do we graph them? What changes does that make on the graph of sine x when I add the 2 in the front or any other number? Well, think about it this way. If we go back to the table, so the period is going to stay the same. So this is for number 1, y equals 2 sine x. The period is going to stay the same, 2 pi. And so that tells me I'm going to use the same values. 2 pi here, if you remember pi, pi over 2, the 0 here, and 3 pi over 2. What changes does that 2 make here? Watch how this changes. So we had 0, pi over 2, pi, 3 pi over 2, and 2 pi. So let's see what changes this does to the graph. When you substitute the 0 in, sine 0, 0, times 2 is 0. Sine pi over 2 is 1, times 2, 2. Sine pi is 0, times 2 is 0. Sine 3 pi over 2 is negative 1, times 2 is negative 2, and the last one 0. So what does that does, you get the y get multiplied by 2, as you notice. It's simply we multiplied the y values in the previous table here by 2. So the 0 stay the same, but the 1 and negative 1, they become 2 and negative 2. So now we are going to plot them here. 0, 0, pi over 2, 2. Pi 0, and 3 pi over 2, negative 2, and 0. So this goes over this way, down, up. So what did that? It stretched the graph up and down like vertically. So then it continues the same way on both ends if you want to graph this. So domain stays the same. What happened? The range changed. The range is from negative 2 to 2. The amplitude changed. The amplitude now is 2. The x-intercepts are the same, y-intercepts the same. Still, it's an odd function. Domain stays the same. So that's what happens. So if we increase that number in the front, it originally was 1 sine x. If it's 2, it stretched the graph by 2. If it's 4, it makes it stretch out by 4. But the x-intercepts, they stay the same. And if we make it 1/2, that will shrink it down vertically by a factor of 1/2. So instead of going up to pi over 2, 1 is going to go up to pi over 2, 1/2. So then the amplitude becomes 1/2 and the range becomes -1/2 to 1/2. Number 2 now, y equals negative sine x. We use transformations the same way as we did back in algebraic expressions and functions. That negative sign tells us to reflect the graph, because what are you doing? You're doing y negative y. In general, if you have xy plane and you have a point, make y negative y, so it becomes down here. So we reflect the graph of y equals sine x about the x-axis. That's what negative sign tells us to do. So this means I need to graph y equals sine x, which we already did earlier. I don't have to go through the process again. So I'm going to just plot the points. So the original function was here, and it was at 1, here, -1. So it goes like this, like that. And then it keeps going. That's over one period. And then down, up, and it keeps going. Now, what I'm going to do, I'm going to reflect this about the x-axis. So this point stays as is. This point up there becomes here. The x-axis point stays as is. The lower point becomes here. That point stays the same. So it's going to come down, up, and down. And again, this keeps going on. This keeps going on. So the green curve is the one for negative sine x. Domain stays the same, range the same, amplitude the same, symmetric about the origin, so it's an odd function, nothing changes. The x-intercept's the same, y-intercept's the same. Third one, y equals sine 2x. Y equals sine 2x. So for the meantime, and I'll come back to this. So x here, what happened? We took, it was originally y equals x. So kind of like when I decided to write this question down, what I did, I replaced the x by or with 2x. And what that does, it divides the period in half. So instead, the period becomes is pi, not 2 pi anymore. And I'll give you a formula how to find that out in a minute. So now this means I'm going to graph it over 0 to pi. So I'm going to assume the pi is here. So what goes in the middle? This is my strategy. You take the middle one, which is pi over 2. And what's exactly halfway between 0 and pi over 2 is pi over 4 by dividing, by 2. This is like 1/2 and 1. So if you add the 1/2 plus 1, that's 3/2. If you divide it by 2, that gives us 3/4. So this is 3 pi over 4. So now we need to find their corresponding y values. So we got a 0, pi over 4, pi over 2, 3 pi over 4, and pi. If we substitute the 0 in, sine 0 is 0. If you substitute the pi over 4 in, you're going to get sine 2 times pi over 4. By 2, 1 by 2, 2. So sine pi over 2 is 1. If you put sine 2 times pi over 2, that's sine pi. Sine pi is 0. And if you put the 3 pi over 4 times 2, that's 3 pi over, that's a negative 1, and that one is 0. So it gives the same values, as sine x, and you might be wondering, wait, but they are the same graph. Well, this is the difference. See, the graph will look exactly the same way of following, and then this goes on and on. You know? So the only thing change here, domain same, range same, amplitude, intercepts, everything same. The only thing change here is that I graphed it over 0 to 1 pi only, not 2 pi. So if I want to graph, so this is kind of like half, the period is half of the graph of sine x, the main function, y equals sine x. So if you want to graph sine 2x on the same graph, it would be just double the length of the graph will be double this one. But it looks the same because I made the magnitude almost same, so it's easier for students to see. But that's what this means. It's just the period became half. So what happened if I make the 2x 1/2 x? 1/2 x. That will make the period 4 pi. It will double the original period. So in general, so you know how to find it out. In general, if we have y equals a sine bx, where a and b are constants, and same thing applies for cosine, then two things to know. First one, the period is always can be found using 2 pi over the absolute value of b. That's the period. And the amplitude, always the absolute value of a. Always the absolute value of that number in the front. And one other thing to keep in mind, it's always the maximum. If you are given a graph and to find the amplitude, it's always the maximum value the graph can reach minus the minimum value that you can see from the graph that can reach, divided by 2. That gives us the amplitude. So if I want to apply it as an example to sine 2x, notice how the amplitude here is the same. The absolute value of the number in the front, 1. So the answer is 1. But the period is not the same as sine x. It's 2 pi over the absolute value of b. b here is what? This is b. Whatever is being multiplied by x. The number being multiplied by x is b. So the absolute value of 2. Absolute value of 2 is 2. So that's why we get the period of pi. Now, another thing to note here, for the amplitude, what was the maximum value the graph reached? It's 1. The minimum value the graph reached is -1. If I substitute into this 1 minus -1 over 2, what do we get? 1 plus 1 over 2. That's 2 over 2, 1. See, that confirms it. Same thing, exactly same thing applies for the graph of y equals cosine x. So now, that's what we're going to do now. We're going to look at the y equals cosine x. How do we graph y equals cosine 2x, cosine x? Same thing. So the period here, it's 2 pi, and you will see that the amplitude is 1. Amplitude is 1. Since it's 2 pi, I decided to go from 0 to 2 pi. And so I take the middle point, middle point, middle point. Notice the more you use them, the faster you become. And I'm going to get their corresponding y values, x, y. 0 pi over 2, pi, 3 pi over 2, 2 pi. Let's see. So cosine 0 is 1. from previous sections. Very important to know. Pi over 2, cosine pi over 2 is 0. Cosine pi, -1. Cosine 3 pi over 2 is 0. And cosine 2 pi is 1. So this is x, y, origin. Teachers always like to see you labeling the x, y, the origin, and placing the points and then the arrows. Do not just graph it without plotting specific points to see where it started, where it ending. So 0, 1 is the first point the graph is going to start at. This is 0 here, and then it's going to go down to pi -1. Then 3 pi over 2, 0, and 2 pi 1. So it's going to go down, up, like this. So that's the graph of cosine over one period. So what happens after that? After that is just, you know, it continues the same way. Again, domain or real numbers. X-intercepts, it's at pi over 2, 3 pi over 2. It's going to be at 5 pi over 2, negative pi over 2, and keeps going on and on. And this can be rewritten as, if you look at these numbers in the front, the 3, a 3, 5, and there's a 1, -1. These numbers are odd numbers. In mathematics, any odd number can be written in the form of 2k plus 1. So 2k plus 1, and then all multiples of pi over 2. So the x-intercepts are at 2k plus 1 pi over 2, where k is an integer. K is an integer. So these are the x-intercepts. The y-intercept, there's only one y-intercept. 0, 1. That's the y-intercept. Domain is all real numbers, range from -1 to 1. This is an even function. Even function. Even function because if we do cosine -x is cosine x from the previous sections. Even functions, and since it's even function, it's symmetric about the y-axis. Symmetric about the y-axis. That's about the graph of cosine. Now we're going to see what happens if we change stuff. Let's say ask us to sketch the graph of y equals 3 cosine 2x. Okay, so I put 3 in the front and 2 where the x is. So now what are we going to do? Well, the first thing, the 3 tells me, I mean, if you want, the amplitude is 3. The opposite value, that 3 in the front, 3. The period is 2 pi over opposite value of that 2 in the front. It's pi. So it's the same thing as we did in sine. So we can go over 0 to pi and just graph it from there. And then from there, after that, it just continues on both ends. So let's see what we can do here for this one. So let's say I'm going to go 0 to pi. Say the pi is here. Halfway is pi over 2. Half of 1/2 is 1/4, so pi over 4. And this is 3 pi over 4. I got the table of values. 0, pi over 4, pi over 2, 3 pi over 4, pi. If you put 0 in, cosine 0 is 1, so that's a 3. If you substitute pi over 4, that's going to look like cosine 2 times pi over 4. By 2, 1 by 2, 2. Cosine pi over 2 is 0, so that's a 0. If you substitute the pi over 2 in, that becomes cosine pi, that's -1. By 3 is -3. And this will be 0. And this one, cosine 2 pi, that's a 1, so that's a 3. So 0, 3, 1, 2, and 3. So it's going to start here. That's the y-axis. That's the x-axis. Pi over 4, 0. This one is -3. So it's going to go down here. Then 0, then again up to about here. That's a graph. So we graphed over a pi period or one cycle, and then from there, as you know by now, it repeats. So domain the same, range is different here. Range is -3 to 3, and then the intercepts change as you can see them. Multiple of pi over 4, odd multiples of pi over 4. The amplitude is 3, period is pi. That's like really enough information about it. And this is still an even function, symmetric about the y-axis. What about if we change the function and sketch the graph of y equals cosine -pi x? How to graph this? Ooh. First thing, I'm gonna start with the period here. What's the period? It's 2 pi over the absolute value of -pi. That gives us 2 pi over pi, which is 2. That's the period. Notice there's no pi in the period. That's the difference between this and all the other graphs that we sketched today. So this is different. So how we're gonna do this if the period is just a number, it's not a multiple of pi? Well, the same thing. So the length of the period or the cycle is 2 units. Think about this way, 2 units. So you can go from 0 to 2 or -1 to 1 or 1 to 3, whatever you like. So I'm gonna always stay within the neighborhood of 0. So I'm gonna go from 0 to 2. Say 2 is here. The period is always on the x-axis. Halfway is 1. Half of 1 is 1/2. 1 plus 2, 3. Divided by 2, it's 3/2. I got 5 points that I need. I'm going to substitute them in and see what I can get. So I'm going to substitute these values into the original function. So 0, 1/2, 1, 3/2, and 2. So if you substitute 0 in, cosine 0 is 1. If you substitute 1/2, cosine -pi. Wait, cosine -pi. Where is -pi? Well, if you remember on the unit circle, if you like to go back and see it, this is 0, that's always the positive, that's the negative direction. So if I want to go this way, that's -pi over 2, if I'm traveling this way, and this is -pi. So I'm landing here, it's like at pi, same terminal side as pi. And we know that cosine pi is -1, so this is -1. If I put 1 in, substitute 1 in, I got, sorry, this was for this one. This was -pi, -1. If we substitute the 1/2, I'll get -pi over 2. -pi over 2 is here. The same terminal side as 3 pi over 2 if you're traveling the opposite direction. And that's 0. So cosine always 0 at this point and this point. Always. So if I substitute the 3/2 in, -3 pi over 2. -3 pi over 2 is going to go, again, this direction. That's -3 pi over 2 is here. So that's going to be 0. And if I substitute 2 in, that will give me cosine -2 pi. Where's cosine -2 pi? Well, you start here and go the negative direction to -2 pi. So that will land you at 0 back, which is 1. Cosine 0 is 1. I got the 5 points. 0, 1. Say 1 is here. 1/2, 0. 1, -1. 3 over 2, 0. And this is 1. And this can go on and on. So what's the difference here? Amplitude still 1. Period, the only difference, the period is 2, just number 2. Domain is all real numbers, range from -1 to 1. The intercepts are different. So the y-intercept is the same, 0, 1. But the other ones, the x-intercepts are multiples of 1/2, odd multiples of 1/2. So 1/2, 3/2, 5/2, -1/2, -3/2. See, it's an even function, symmetric about the y-axis. One thing to do, I recommend you do is, even if you never used it before, any function you try to graph, especially in trig functions, it would be nice to check the work using Desmos. It's a software, free software, you can use it to graph functions. So you can always check the work on Desmos to see if your graph matches the Desmos graph, just to check your work. And that's what this section is really about.